In today's lesson, we're going to learn about perpendicular lines and what we know about them. So we need to know what perpendicular bisectors are, as well as the distance from a point to a line. So we're going to start with those definitions. We know perpendicular and we know bisector. To be perpendicular means they make 90-degree angles, and to bisect is something, or to be a bisector is something that cuts it in half. So a perpendicular bisector is a segment of a segment is a line perpendicular to a segment at the segment's midpoint. Okay. The other thing we need to know is the distance from a point to a line. So the shortest segment from a point to a line is perpendicular to the line. The fact is used to define the distance from a point to a line. So that is the length of the perpendicular segment from the point to the line. So to see that in a picture makes a little bit more sense. So let's look here. So in this picture, if we wanted to see a couple things we notice, we see that A is a point on its own out here, and we have a right angle. So we've got some perpendicular lines. That's something good to notice. So it says to name the shortest segment from point A to line BC. Well, we just learned that the shortest distance from a point to a line is the segment that is perpendicular. So the shortest distance would be segment AP. It says write and solve an inequality for x. So this is kind of new. Notice that we have two segments here, and one is shorter than the other. So we don't know how long AC is, and but we do know that AP must be shorter because that's the shortest distance from the point to the line. So we've established AP is the shortest segment, and so AP must be bigger, or no, must be smaller than AC. AC should be greater than the measure of AP. Now if we substitute in their measures, we get that x minus 8 is greater than 12. Now we solve inequalities just like we would solve an equation. We're going to add 8 to both sides and get that add 8 to both sides and get that x is greater than 20. So any number bigger than 20 will work in the spot for x. Okay, let's try one more. In this one, name the shortest segment from point A to line B. So we said that the shortest segment will be the one that's perpendicular. Notice AC is not perpendicular, so AB, which is perpendicular, should be our shortest segment. And to write an inequality, we want our shortest segment to be less than the other segment. So I know that AC should be bigger than AB, so my inequality is going to open towards AC. Now we'll take their measures. AC is 12, and AB is x minus 5. So if we plug their measures in, we solve just like we would solve for x before. We're going to add 5 to both sides. And we're going to get that 17 is greater than the value of x. Alright, now we're going to look at a couple of theorems that have to do with perpendicular lines. Notice only one of these has a title that you can use in a proof. The other ones you would just shorthand, and you can write, like if you're going to use this theorem as a reason, instead of it having a name, you'll have to write in this whole thing. So they show you what this theorem would look like if you shortened it and used symbols and things. But it says that if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So let's try that again. Two lines are intersecting. They form a linear pair where the line with their two angles being congruent, and we conclude that that means that the lines must be parallel. Okay, the next one says in a plane, if a transversal, so remember a line that goes through two other lines, Q in this case, is perpendicular to one of the two parallels, then it is perpendicular to the other. So if these are parallel and Q is perpendicular, this theorem tells us that, or to N, that it's also going to be perpendicular to Q. And our last one says if two coplanar lines are perpendicular to the same line, then the two lines are parallel. So it's kind of the flip. instead of seeing that one line is perpendicular to one of the two parallels, we're going to say it backwards. If the line is perpendicular to the two lines, then they must be parallel. We may have to read through those a couple times for them all to make sense, but we're going to try to do a proof or two so we can see how they might be used. So, this proof says given R is parallel to S, and we know that 1 is congruent to 2, we want to prove that R is perpendicular to T. So we're going to start with a partly filled in proof and see if we can come up with the missing pieces. So start to remember the pieces of a proof and the things that always stay the same. So we always said, what do we always start with? Well, it says R is parallel to S and 1 is congruent to 2. How did we know that? Well, it says that it's given, which is what we always start with, so our reason is going to say given. Now it says we're going to use corresponding angles postulate, which said that corresponding angles are congruent. So if we look in the picture, we want to find, do we have any corresponding angles? Remember, corresponding angles are matching positions. Well, when I look in this picture, I see that 2 and 3 are in matching positions. So I think we're probably going to say that 2 is congruent to 3. Okay, our next step says we're going to use the transitive property. Remember, the transitive property, we're looking for a connection. So we have two congruent statements, and I see that angle 2 is a part of both of them. So if we connect those two with angle 2, we can say that 1 is congruent to 3. So now that 1 is congruent to 3, how do we know that R should be perpendicular with T? Well, one of the proofs we just learned, or one of the theorems we just learned, said that two intersecting lines form a linear pair. If two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. So that was one of the ones that didn't have a name, so we just wrote out the sentence as short as we could, so you can use as many symbols as you want to. Remember, this arrow means if I have this, then I can say this. So if two intersecting lines form linear pairs of congruent angles, so we said that 1 is congruent to 3. Well, in our picture, those are a linear pair, and we just said they were congruent, so we can say that those two lines are parallel. Good. So we're going to try one more proof. This one's a little messier, so you may want to take another second or two to look over the picture. It says that angle EHF is congruent to angle HFG. So you can see in the picture they put the symbols in there for you to know that. And they also told us that line FG, upside down T, means is perpendicular to GH. So it shows us that in the picture with our right angle symbol. And we want to prove that EH is going to be perpendicular to GH. So here's our proof. We're just going to fill in the missing pieces. So like I said, we always start with the given. Notice though we have two givens. So since we have two pieces of given information, it looks like we're going to split those apart. So let's start with the one that we know, or the first one they give us. So we're going to start with EHF is congruent to HFG. So it says that with these two being congruent, the next statement says that EH is parallel to FG. So we're trying to decide why, if these two angles are congruent, do these two lines have to be parallel? Well, if you remember with our converse theorems, that if these two lines, if we look at these two lines, well, the angles that we have congruent are on opposite sides of what could be a transversal, and they're inside those two lines. So if alternate interior angles are congruent, then we should be able to say that the lines are parallel. So that was the converse of the alternate interior angles theorem. So that's kind of like something we used from the last unit. Okay, the next line says given again. So since we already used this first piece, we're not going to reuse it. Now we're going to use the second piece of given. So FG is perpendicular to EH is going to be our next given. And our next one says the perpendicular transitive theorem. So we're trying to figure out what the perpendicular transitive theorem says. We want to look for a connection. So I see a connection here. So if these two are parallel, if FG is perpendicular to GH, then GH should also be perpendicular to EH. Another way to figure that out, with a proof, we asked ourselves, what do we always end with in our proof? Our last statement should always be our conclusion, or what we're trying to prove. So it fits both ways, that what we're proving fits here, and because of the perpendicular transitive theorem, that EH is now perpendicular to GH. All right, we're going to look at one more little example, looking for an explanation. So let's read this together. It says a carpenter's square forms a right angle. A carpenter places the square so that one side is parallel to an edge of a board and draws a line, and then draws a line along the other side of the square. Then he slides the square to the right and draws a second line. Why must the two lines be parallel? So if we tried to think about the proofs that we had, notice that if this makes a right angle, we're saying that if this that the metal side is always perpendicular to the edge of the board. So if this is perpendicular here, and I move it over and it's also perpendicular here, we had a theorem that says if two lines are perpendicular to the same line, then those two lines should be parallel. So in an explanation, both sides are perpendicular to the edge of the board, because that's what the squared makes. So these are both perpendicular, and if two coplanar lines, so notice they're on the same board, they're on the same plane, if they're both perpendicular to the same line, this edge, then those two are parallel. So the lines must be parallel to each other. So you've got some practice in class, and I'll see you later.